Then let's take a look of a related problem here. Okay. Yeah, let's do this again with a different interpretation and see if we can get a better idea of what it is about. Okay. So recall that function. So what is a function? So a function is a mapping that we have some items here from some set S to another set, let's say T, such that for each object here it receives one value in T. Is that okay? Maybe let's say there are 3 objects here, and then let's say there is a 4th object here. Is that okay? So for instance, the problem that we are looking at is we will be looking at this S to represent the set of objects you may be looking this set T as the set of boxes that we have. And then this tells us that, okay, A is going to be going to box 1, B is also going to box 1, C is going to box 2, and then D is going to box 3. Is that okay? Okay. Now, the requirement for a function is that everything on this side, you need to know where it goes. But there is no restriction about what happens here. Maybe you can have something like a 4 here. We can have a 4 here. Okay, such that it is not being mapped from anyone. Is that okay? Okay, so there are different kinds of functions. Okay, so in general, you can have all the ways of mapping that you like. But then there are injections. So function, there are injections. Injection means that everything here is only mapped by someone, only once. Okay, so this is called injection, at most once. So it's like you go to the hospital when you are sick and then you have a shot. So this is called an injection. So the nurse won't shot you twice at the same position. Am I correct? Because otherwise it's hurtful, right? So in that case, injection is like, if I have the first shot, I choose here. Then if I need to have a second shot, I will need to find another place to take a shot. Is that okay? So this is called surjection. There's another type of function that is also special. It is called, injection, So there is another type of function that is special. This is called surjection. So surjection means that everything on this side has to be used. So sur is like surface. It covers all the surface. So everything here has to be covered. Okay, has to be used. So that's called surjections. And then if a function is both an injection and surjection, then it becomes the case that everything here is mapped exactly to one thing here. And then everything here is mapped by exactly one thing from here. Am I correct? So in that case, there will be a one-to-one correspondence between the set S and the set T. So in that case, we have a special name for that. That is called bijections. Is that okay? So now, we want to count surjections, the number of surjections. And you will see exactly why we want to count the number of surjections. Because it is exactly the number of ways to distribute distinct objects into distinct boxes such that all the boxes has to be used. Is that okay? Okay. So let's count the number of surjections. Okay. So the size S here is R here. So the size S here, so there are R objects here, and let's say there are N objects here. Okay. Now to do so, we are going to, hopefully, we will arrive at this formula. This formula has something plus and something minus. If you look at it, the first term here that we have is a plus term. When j is equal to 0, this is going to be plus. J is equal to 1 minus, plus, minus, plus, minus. So does it occur to you anything that when we are doing counting, you have something like a plus, minus, plus, minus, plus, minus? Any counting problem, we will be using a minus. So rule of sum is plus, rule of product multiply, right? Rule of division, so what is rule of division? We partition things into groups such that each group has the same size, then division. There's one thing that I didn't tell you, but it's so natural that you should have heard of it or used that already. We need to use minus. Minus means what? We overcount something so that we need to take away. So what is that? Any idea? So in what kind of counting problems that we are going to overcount? We may be counting something here, we may be counting something here, and then why do we need to overcount? What happens? We take away something that we overcount. What's that? Any idea? Okay. I draw a diagram, you know. Okay, there is I believe every one of you have heard of it. This is the principle of inclusion and exclusion. So we have, let's say there is a set A here. Let's say the students here in our class, let's call it set A. Set B, let's say set B is the student here that, okay, A is, let's say, the student here in our class. So it represents a certain group of students. And then B represents what? Let's say B represents the PhD student in our department. Okay? And then we want to count what is the total number of PhD students in our department together with the student in this class. Then how do we find the number? We get the total number of students in this class plus the total number of PhD students in our department. We add them up together, but then we need to minus the number of students that is both in A and B. Is that okay? If you have, I believe, just take a vote. If you have not heard of inclusion exclusion, could you please raise your hand? No. Okay, good, excellent. So here, so let me just review a little bit. So here we want to look at what is the size. So I need some set notation. A is a set, B is a set. And then I want to count what is the size of A and B together. So A union B would be a new set that corresponds to this, and then we have this one. And then it turns out that it is equal to the size of A, okay, plus the size of B, and then important thing is minus the size of the intersection between A and B, the common part of A and B, okay? Now, inclusion exclusion can be extended when we are talking about more than 2 sets, 3 sets, 4 sets. So if we have a C, so let's say this time we have a C here. Let's call it a C. And then we want to count what is the total number of things in any one of these sets. So we want to get A union B union C. We want to get the size of this one. Then this will be equal to the size of one single set. Is that okay? Minus the size of the intersection of any 2 sets. So minus A intersect B minus A intersect C minus B intersect C. Is that okay? And then add back. So this is overcounting. So we need to remove the overcounted part. but then we remove too much. So we need to add back. Add back what? Add back the intersection of all the three of them. Is that okay? Okay, so let's count surjections. Now. Actually, there is one more thing that I need. This is the De Morgan's law. So let's say there are still more people around. So that let's say this is the whole universe. Let's call it U. That represents all the things here. And I want to count those things that is not in A or B or C. Then what does that be? Then it's easy. Then this is just U minus the size of this one. Is that okay? So but then I want to make sure that we all recall this one. So if I want to get U minus A union B union C, it is going to be counting. So De Morgan's law says that this is the complement of A union B union C. And the complement of A union B union C is going to be not A intersect not B intersect not C. Okay, so these are the two things that I need you to use. Okay, that's it. Okay, otherwise we should be fine. Let's try. Okay, let's try. So how should we count? Okay. So I'm going to define something. Okay. I'm going to define A1 to be the functions. So we assume that we are talking about only functions that has S part with R items and then T part with N items. Is that okay? From S to T, R objects to N boxes. Okay. And then A1 corresponds to, there can be a lot of functions. So let's say, give me some time. Okay, let's say A1 to be the functions that do not map to. Okay. That do not map. Let's try this one. Let's call it. Okay. Let me see. Okay. Okay. A2. Let me see. Does not map to one. Which one is better? Let me see. Want to count. Does not. Okay. Does not. Okay. Let's try. Okay, functions that does not map to 2 and so on. And let's say we have AN represent the set of functions that do not. Okay, do not. do not map to n. Okay, so I'm going to define this set a1, a2 up to an. So each represents a set of functions. Okay, let's see. So these functions are something that we do not like. We do not like a1. We do not like a2. We do not like an. Because these are the functions that should not be counted. Okay? So, but still, we need to get how many are there. So we want to know what is the size of this a1 union a2 union a3 up to an. So if we can get the size of this one, then we use all the functions, the total number of functions that we can think of, minus this one, then this will be the number of functions that we want, or the number of surjections that we can have. Is that okay? If you are okay with what I'm going to, I'm talking about so far, could you please raise your hand? Okay, good. So these are bad guys. I don't want A1, I don't want A2, I don't want A3. But these bad guys are easy to count. So I'm going to count the bad guys first. After counting the bad guys, we know how many good guys are left. Okay? So let's count this one. Let's focus on counting this one. Now, this is what? This is the inclusion-exclusion principle that can help us to solve. This is the problem that we can use inclusion-exclusion principle to solve. So this size would be, okay, so let me use the more space again. So you can also think about this together. Okay. Okay. So think about this together. So the number, so this is A1 union A2 union A3 up to AN. Now by inclusion exclusion, this will be equal to, so we get the size of each of them. Is that okay? And then minus what? Minus, so we have a plus, minus, we get any combination of two intersect. Any combination of two. Is that okay? And then we need to add back. This time, let's use red. Add back the intersection of any combination of three. Is that okay? And so on and so forth, up to the case where we are considering the intersection of all of them. So it is plus, minus, plus, minus, plus, minus. So in the end, it is going to be plus. It depends on how many terms that we have. So it is going to be minus 1 to the power, if it is odd number, it is a plus. Even number, it is a minus. So it depends. So when we are intersecting n of them, so it is going to be n minus 1. Okay? Or n plus 1, whatever. Okay? Times times the size of A1 intersect A2 intersect AN. Okay? Is that okay? Now, how many things are there? So what is this? What is A1? What is the size of A1? A1 counts the number of functions that does not map to 1. So what does it mean? So A needs to find a place, but it cannot be 1. B needs to find a place, it cannot be 1. C finds a place which cannot be 1. D needs to find a place which cannot be 1. So how many ways are there? A can have n minus 1 choice, am I correct? B can have n minus 1 choice, C can have n minus 1 choice, D can have n minus 1 choice. R things, each one of them has n minus 1 choice. So each term here is going to be equal to n minus 1 to the power r. Is that okay? This one, the same, n minus 1 to the power r. This one, n minus 1 to the power r. Good, so good. We have something n minus something to the power r. This is what we are looking for. How many things are there? So there are n items, am I correct? So the blue part, so this blue part, we get what? We get n items. N actually comes from n choose 1. And then each one has n minus 1 to the r ways to choose. Is that okay? Okay. Now, if you are okay with this, then let's count this time, the black part. So what is each term of this black part? I cannot use 1, I cannot use 2. Very good. N minus 2 to the power r. Is that okay? So this black part will give us, minus 1. And then how many black things are there? There are n choose 2 black things. Is that okay? And then each one of them will have a value n minus 2 to the power r. Is that okay? Good. And then the red thing, yeah, we now know. The red thing, this is going to be plus n choose 3 times n minus 3 to the power r. Is that okay? Is that okay? And then orange. What is orange? I cannot choose 1, I cannot choose 2, I cannot choose 3, I cannot choose 4, I cannot choose n. Impossible, right? Impossible. Because it is a function, we need to choose something. So it is actually 0. And then this 0 actually corresponds to what? So I left out the minus 1 to the power n minus 1. So it is going to be n choose n times n minus n to the power r. Is that okay? I'm just adding this there. Okay? Good. Bad things. Bad things. So we are going to talk about good things now. So how many good things? Okay, so the number of suggestions is equal to good thing, the number of all possible functions minus this size a1 union a2 union ... up to an. And then what is the number of possible functions that we have? I have n choice for A, n choice for B, n choice for C. So this is going to be n to the power r. Is that okay? Minus. So we have minus, then this is going to be minus n choose 1, n minus 1 to the power r, plus n choose 2, n minus 2 to the power r, minus n choose 3, n minus 3 to the power r, and so on and so forth. Is that okay? This is what we want. This is how we can interpret this one using a combinatorial argument. Okay, if you understand what I'm talking about so far, could you please raise your hand? Okay, very good. Interesting, yeah. Don't worry, no need to memorize it. Yeah, just get a feeling. Okay, this can be solved. And then we are going to have a break soon, but I have one question for you. I claim that, okay, So this number of ways represent a certain thing, a certain way of counting things. So I claim that this number of ways is divisible by n factorial. So it is always divisible by n factorial. And I need you to think about this during the break. Okay, so let's have a 15-minute break, and then we come back and we continue the discussion. Okay, so everyone understand what I'm talking about, right? So this term, this thing, no matter what happens, so you fix r, you change the n, and in any case, it is going to be divisible by n factorial. Okay, so let's take a break and then think about this.